Hi everyone, I'm Jigyasa. I work as a software developer at Autoverse, a company that specializes in making VR training. Today, I'm going to speak on the topic using AR, VR, and emerging technologies to transform education and training. I'm going to be presenting my research, which I did as a part of my undergraduate thesis. So, let's start by looking into the benefits of virtual reality training. So, the first thing is that it provides an immersive learning experience. In virtual reality, you can completely mimic the real world scenario, which allows users to train in a very real environment which engages them completely without facing any real world consequences. VR also provides a safe environment for high risk trainings in high risk industries like aviation, healthcare, construction, where mistakes can lead to severe consequences. So, trainees can train in a safe and risk free environment and they can repeatedly train before they're ready to for the real environment. VR also leads to enhanced retention and engagement as we engage more number of senses in VR as compared to what we would do in traditional training, and that has proven to lead to enhanced retention and engagement. It is cost effective over time. So although the initial cost of setup of VR might be high, it does it does help to reduce some repetitive costs like equipment maintenance, trainers, traveling to the training location. So all of these costs are cut in the long run through VR training. VR also provides remote access and scalability as trainees can train from any part of the world, and we can train as many people as we want. So it's very scalable and it can be done remotely. Now, as we are talking about other emerging technologies that we can be used with VR, in this research, I used reinforcement learning, which is a common machine learning algorithm which is used in games and virtual reality. So, what exactly is reinforcement learning? As I mentioned, it's a machine learning where an agent learns to make decisions by interacting with its environment. The agent receives rewards and penalties for its actions, and the goal of the agent is to maximize its rewards. And how does it work is that the agent takes an action and in return it receives a response from the environment, and that response may be positive or negative. That is, either it can get a reward or a penalty, and in return the agent alters its future actions in order to maximize the positive reward. It's basically like learning through trial and error, which is something that we as humans also do. RL is important because it's ideal for complex and dynamic environments where predefined instructions aren't enough. And it's used extensively in VR, games, robotics, autonomous vehicles, and many more such industries, which enable systems to adapt and improve performance over time. Now we are going to look into a methodology which is called procedural content generation. So, what exactly is procedural content generation or PCG? So, procedural refers to a set of instructions or procedures in coding which can be used to generate content. Basically, we're using coding to generate content. And what exactly is this content? Content can be anything that is presented in front of the user. In terms of games or virtual environments, it can be the textures, it can be the objects, the layout of the levels, it can be the music or the behavior of the AI, the dialogues, the story. Anything that is procedurally generated is called procedural content generation. And this has widespread application across data visualization, dynamic advertising, and video games, and by extension, of course, virtual reality as well. So, as I mentioned before, that it's commonly used in video games as it generates diverse content such as levels, character models, textures, sounds, and AI behaviors, reducing the manual effort of content creation. And there are various ways of using PCG. So, either we can create content from scratch, that is, things like textures of objects which are created right from the very initial stage, or let's say we have a list of pre-made objects, or we have a repository of pre-made objects, and those have to be the layout of those objects have to be decided in the scene. So the layout can be procedurally generated. So let's dive a little deeper into this topic and see how other emerging technologies can be used in integration with virtual reality to produce more effective trainings. So classical virtual reality training simulations, they do exist, but they suffer from a limitation. In most of the VR trainings which we have, it prepares users for a very specific kind of disaster or a very specific kind of scenario. Let's say if we have VR training for earthquakes, in that it will only show ceiling debris falling from one particular place in each iteration of the training. Or let's say in a fire disaster, the VR training of a fire safety module, it will show only a specific object catching fire in every iteration of the training. But the very nature of disaster is that it's unpredictable, it's uncertain, and we cannot have just one specific kind of training and expect the user to be trained or feel confident to deal with a certain disaster scenario. The solution is obviously to have variations in training and have various kinds of scenarios where maybe the user is placed in a different location, or there is a different kind of disaster, or the disaster happens at different locations. But manually creating such variations in virtual training is a very time consuming and monotonous task, not just for the developers but for the designers as well. In such a situation, if we were to use these emerging technologies like AI, machine learning, or and programmatically generate these variations, then that would decrease the development time, it would decrease the workload to a great extent, as well as the resulting training simulations will be much more efficient and effective. And with rapid advancements in VR technology right now and rapid advancements in head mounted displays, the VR hardware is also quite capable these days. VR training has become easier to adopt, easier to scale, and very practical to use. And it allows us to do virtual reality safety trainings in a much more cost effective, immersive, and safe manner. So now let's look into the proposed system. So we proposed a virtual reality training simulation to simulate fire disasters, and the concept is that the user is placed in a room where each of the furniture object, it's procedurally generated using a reinforcement learning based procedural content generation algorithm. And as I mentioned, that the reinforcement learning agents in this scenario are the furniture objects, and some of these furniture objects are flammable, and one of these objects will act as the fire source, the place from where the fire starts. It can be a candle which catches fire on a curtain, or it can be a lamp which fuses, maybe a stove that is left burning. And the location of this fire source is determined using the pseudo random number generator algorithm. We'll look into this algorithm further, and the rest of the reinforcement learning agents, they will position themselves in the room in a way that places the flammable objects at an optimal distance from the fire source, while the other objects are placed in a logical manner in the scene, the way you would actually expect these objects to be in a general real world environment. Now, these dynamic environments are regenerated each time the application restarts, ensuring a new layout in every session. This is the architecture of the proposed system. In the top layer, we have the Unity ML Agents toolkit, which is a toolkit which allows developers to give machine learning capabilities to 3D environments. And as it's machine learning, it works on the Python virtual environment, which is one component of this layer. Then the other component is the reinforcement learning algorithm, which consists of hyperparameter tuning, the reward function, and the procedural content generation algorithm. Now, the second layer is the Unity game engine itself, which consists of 3D models which are loaded in the scene. the virtual environments, which are the Unity scenes, the XR interaction toolkit, which allows us to give VR capabilities to the 3D environment so that these environments can be played on virtual reality headsets. And the last component is the physics engine, which is basically a feature of the Unity 3D game engine, which allows us to give physics capabilities like rigid bodies, colliders, kinematics, gravity, stuff like that to the objects in the scene to make it look more realistic. And the bottom layer is the hardware itself, the hardware on which we'll deploy our virtual reality training. It can be any VR headsets. And for this demo, we had used the MetaQuest 2. Now let's dive a little deeper into the PCG algorithm. For for this research, we presented a 3-layer PCG architecture, um, in which the bottommost layer is the pseudo random number generator algorithm, which we saw before. And that is basically an algorithm which generates a random number, and that random number is used to determine the spawn position of the user as well as the initial spawn position of the fire source. Now, the next layer is the reinforcement learning PCG algorithm, which is basically the algorithm which controls all the furniture objects in our 3D environment. And it is used to this reinforcement learning PCG algorithm has information about the environment so that it can position all the furniture objects in a logical manner. Now, the topmost layer consists of the fire algorithm. So, even the fire in the scenario is procedurally generated. So, the spreading logic, that is, which objects the fire should spread to, at what rate the fire should spread, the change intensity, which is the rate at which the fire is increasing, or the extinguishing. If the user starts extinguishing the fire using a fire extinguisher, at what rate the fire should extinguish. And even if the user does not extinguish the fire completely, it starts regenerating. So, all of this is taken care of by the fire algorithm, which consists of the top layer of our 3-layer PCG architecture. So, as we're talking about machine learning, of course, machine learning uses data sets, but reinforcement learning, it stands out for use in virtual reality and in games because it collects data from the environment during the simulation itself. So, in reinforcement learning, we do not need to collect any data beforehand. It collects data from its environment during the simulation or the training itself. So now, what kind of data is collected from this virtual environment? So things like the XYZ coordinates of the fire source or the XYZ coordinates of each furniture object. This is the kind of information that the reinforcement learning algorithm uses to train itself and to take the next action in expectation of a reward or a penalty. Even the velocity of the reinforcement learning agents along its x and z axis. So there is a certain velocity associated with each object which allows it to move around in the environment and place itself when the application loads. So that information is also fed into the reinforcement learning algorithm, and it collects this data during runtime, which is why this algorithm is preferred over other machine learning algorithms like supervised and unsupervised learning algorithms for games and virtual reality. Now, here's a list of the reinforcement learning agents that we have in our environment. So, the first is the fire source, which is the lamp. This is acting as the fire source in our virtual environment. This is where the fire starts from. Next is the sofa, which is also a flammable object. There is a huge shelf, there is a carpet, there is a media table, and there is a sculpture table. So all of these are reinforcement learning agents. All of them have velocities, and the position of these objects in the room is decided by our reinforcement learning PCG algorithm. So over here you can see 4 layouts that were generated by the algorithm. As you can see, the lamp is always placed close to the sofa because the sofa is a flammable object, and the huge shelf is always placed against a wall, as it is in real life as well. So the algorithm takes care of these things. All of this information is fed into the algorithm, and that acts as the data. And these are just 4 layouts out of the many layouts that this algorithm generated. Now let's look into some of the features and the actual game flow of the prototype. The first feature is the wrist UI, which is basically a task checklist which is given to the user attached to the left controller, which they can toggle on and off using the menu button on the left controller. This checklist consists of 5 tasks which are designed to be completed by the user in order to pass in this training. And these 5 tasks are as follows. Task 1 is to locate the fire source. Now, using the PRN algorithm, the user is spawned in a random room in the virtual environment, and there will be a smoke alarm in the background, and the user must listen to the smoke alarm and move around the environment to find the source of fire. They can use their the joystick on their controllers to actually move around in the environment. Their second task is to locate the fire extinguisher. So there are signs which will lead the user to the fire extinguisher, which they have to then grab and bring it to the place where the fire is actually occurring. So that's task 3, basically, to grab the fire extinguisher. And as soon as they grab it, they get instructions on how to basically operate that fire extinguisher. Now, task 4, as I mentioned, is to bring the fire extinguisher to the disaster area. Now, as soon as the user does so, they will get on-screen instructions again to aim the fire extinguisher and keep pressing the trigger button to extinguish the fire, which is our final task, that is extinguish the fire. And using our procedural generation fire algorithm, the fire intensity decreases with a certain rate as the user extinguishes it, and if they don't extinguish it completely, it starts regenerating. Now, we also have an alternate game flow in case the user fails to actually extinguish the fire, and if the fire spreads to such an extent that it becomes very dangerous and kind of impossible to extinguish at that point, we have a failure mechanism in which the user needs to drop everything and evacuate out of the scenario. So using with the help of the exit signs, they are supposed to get down the stairs and leave the building immediately. And even if they fail to evacuate, they get a final warning, and after that final warning, it's game over. Basically, they have failed the training and they have to repeat it in order to pass. Now let's look into the video of the prototype. So the user is spawned in a random room and there is a fire alarm in the background. They have to use the controllers to move around and locate the fire source. Now that they've located the fire source, they get a warning and the instruction to locate the fire extinguisher, which is outside the apartment, and they have to take help of the exit signs and actually find the main door of the apartment. And as you can see, the task list, it gets ticked as soon as the user completes a certain task. Now that they've located the fire extinguisher, they're supposed to grab it and bring it to the fire disaster area. Now you can see as soon as they brought the fire extinguisher, they got next steps on how to extinguish the fire in the scenario. The numbers that you see on the wall is actually the intensities of the fire, which ranges from 0 to 1, and we have to bring all of those intensities to 0. They have to keep pressing the trigger button in order to extinguish the fire. And as you can see, because of our fire algorithm, you can see the fire slowly extinguishing. There's a congratulatory message once the user is done. Now we are going to restart the training and show the alternate flow where the user evacuates out of the building. So they just need to follow the exit signs as the fire has spread too much and they need to get out of the building and save themselves. They get down the stairs and this is the main door which leads them out of the building. So, findings and interpretation. We were able to generate dynamic environments every time the application starts. Now, the furniture objects in the scene, they are not placed all together at once. In fact, they are placed one by one. And because of this subsequent placement of each subsequent object is more sensitive about its environment and has a greater number of variables to take into account while deciding its position in the environment. So each agent is smarter than its previous one and has more data to work with. Our system is cost effective. It provides a safer alternative to real life fire safety drills and it is able to generate many variations in training. And the RLPCG agent, the algorithm that we used, it outperforms other RL agents in literature in terms of shorter training time, fewer steps of training, and more number of agents with limited processor capabilities. The future scope of this research is to expand this method to procedurally generate dynamic training scenarios for other disasters like earthquakes, floods, and tornadoes. We would also like to integrate with other immersive technologies like augmented reality and mixed reality to increase the level of immersion and enhance the experience of the trainings. We would also like to use other emerging technologies like generative AI and natural language processing to make the experience more realistic and improve the storyline of the training. We also plan to conduct a user evaluation study to understand the effectiveness of this training with end users and also collaborate with disaster management organizations for testing in real world scenarios. Here are some references, you can check them out. And here's my LinkedIn. You can connect with me if you would like to talk further about this research or any other topic of virtual reality. Thank you so much for listening to me, and I'm really happy to be a part of this international conference on virtual reality. Thank you.